Hello everybody, welcome back to another lesson on sequences and series. Today we are going to be investigating geometric number sequences. Before we look at our concept map for today, I'm going to ask you a question. Have you ever thought about patterns that occur in everyday life? One pattern that we didn't all see coming was the corona pandemic, where there was the exponential growth of corona cases. Now, we didn't even realize that that was a pattern until we started to see the graph and the exponential graph, but that itself is a pattern in real life. So today we are going to be looking at geometric number sequences. Let's have a look at our concept map. So everybody, in this first part of today's lesson, I'm going to define what a common ratio is, and a common ratio itself is the foundational characteristic of a geometric sequence. A bit later, I'm going to define the general term for a geometric sequence so that we can calculate term values and term numbers. Before I get into the specifics of common ratio, I'm going to do a little bit of revision on pattern terminology that's really important for us to have at the back of our minds when working with any type of number pattern. Let's have a look at some of those definitions. So the first one I'm going to talk to you about is a term number. Now, please remember that that refers to the position of the term in the sequence. So Tn is the nth term of the pattern, where n is the term number. So everyone, if I have T1, and we can see over here that n is equal to 1, this is the first term of the pattern. T3 will be the third term of the pattern. So the term number is indicating the position the term has within the pattern. So if I say T7, that is the seventh term in the pattern. Let's have a look at the next definition. So the next one is term value, and that refers to the actual value of the term. So we're going to have Tn equal to a specific number. So if I say that T7 is equal to 334, that means that the value of the seventh term is 334. So the term value and the term number are different to each other. If I say the fifth term of a pattern is 100. T5 is my term value, my term position, and 100 is the actual value of the term. So T5 is the term number, and 100 is the term value. So please make sure you know the difference between term number and term value. Let's have a look at the next slide. So the next definition is the general term. So the general term is a mathematical expression that describes the sequence and that generates any term in the pattern by substituting different values for n. So the general term allows me to calculate term numbers as well as term values. So we are now getting into the main principle, the main definition, the most important thing of a geometric pattern, and that is a common ratio. Before I talk about the common ratio, I just want to remind you that before geometric sequences, we do arithmetic sequences. And arithmetic sequences have a common difference, and that is when there is a specific number that is constantly added or subtracted between successive terms. And a common difference is the main characteristic of an arithmetic sequence. A geometric sequence has a common ratio. Let's look at the board to see the definition of a common ratio. So, a common ratio refers to the factor that each term is multiplied by in order to get the next term. So this is a specific number that I multiply each term value by to get the next term. So let's have a look at our first example. We've got a pattern that goes 3, -9, 27, -81, 243, -729, and 2187. If we are looking for a number that each term is multiplied by to get the next term, we can actually see that each term has been multiplied by -3, because 3 times -3 is -9. -9 times -3 is 27. 27 times -3 is -81. So for this pattern, I can actually see that my common ratio is -3. So just a reminder, this is the number that each term value is multiplied by to get the next value. So a common ratio is the main property of a geometric sequence or pattern. Doesn't matter if you use the word sequence or pattern. So this is the main property of a geometric sequence. Great, everyone. So I hope that everyone's okay with what I've done so far. I've discussed some pattern definitions, and I have defined what a common ratio is. It is the number that each term is multiplied by in order to get the value of the next term. When we come back, we'll be looking at how we get the nth term for a geometric sequence. I'll see you after the break. Welcome back, everybody. In this portion of today's lesson, I'm going to be talking about how we can actually work out the common ratio of a geometric sequence, as well as the nth term for a geometric sequence. After that, we're going to look at an example where we can actually make some calculations using the nth term of a geometric sequence. Let's have a look at how we work out the common ratio. So we have just discussed that the main feature of a geometric sequence is the fact that there is a constant or common ratio. So we discussed that that is an actual number that each term is multiplied by in order to get to the next term. So if I give you the pattern 2, 4, 8, 16 going on, I can see that each term has been multiplied by 2 to get to the next term. So that, in fact, is the common ratio. So if I want to actually calculate the value of the common ratio, because sometimes in an example, it might not be so obvious. For this example, we can kind of see immediately that 2 has been multiplied by 4, and 4 has been multiplied by 2, 8 has been multiplied by 2 going on. So we want to see if there's actually a concrete way that I can calculate the common ratio. The common way that I write down the common ratio is term 2 over term 1. So just a reminder, this is the value of term 2 over the value of term 1. For this pattern, we can see that the value of term 2 was 4, and the value of term 1 is 2. And 4 over 2 is positive 2. So we can see that the common ratio is 2. I can also confirm my common ratio by saying term 3 over term 2. The value of term 3 for this pattern is 8. Then I'm going to divide that by the value of term 2, which is 4, and that gives me a common ratio of 2 again. So I'm hoping that everyone can see that we can calculate the common, sorry, this says common difference, guys. It's supposed to be common ratio. We can define the common ratio to be the term value over the term value that comes before it. So over here we did term 2 divided by term 1, then we did term 3 divided by term 2. It's always going to be the term value over the term that comes before it. So Tn over Tn minus 1. The next thing that we are going to do, everyone, is we are going to find a way to actually generate the nth term for a geometric sequence. We know that in a pattern, we often call the first term A. So in this case, T1 would be equal to A. So I'm going to write that down. So we're going to have T1 is equal to A. And we know that each term of a geometric sequence is multiplied by the common ratio to get to the next term. So term 2 will be AR, because it's going to be the first term multiplied by R. Then to get the third term, I'm going to take the value of the second term, but I have to multiply it by R again. So T3 will be equal to AR squared. Term 4 will be the value of term 3, which we saw is AR squared. But again, I have to multiply by the common ratio to get to the next term. So I'm going to multiply by R again, which means the term 4 would be equal to AR cubed. I'm just going to swap my color, so hopefully it's a bit easier on your eyes, guys. The value of term 4 is AR cubed. And in order to get term 5, I have to multiply it again by the common ratio. So term 5 would be AR to the power of 4. So we can see that each time I am multiplying the term that comes before the present term by the common ratio, because we know that the common ratio is the main characteristic of a geometric sequence. So we can therefore say that the nth term for a geometric sequence can be written as Tn is equal to A times R to the power of n minus 1. Now you might be asking, why the n minus 1? If I go back to my previous slide, I can see that each time the power of R was 1 less than the term value. So here we can say that there was R to the power of 0, because we know that that has a value of 1, because anything to the power of 0 has a value of 1, so that means that R was to the power of 0. Here, R was to the power of 1, which makes sense because this is 1 less than the term value. For term 3, R was squared, and that is 1 less than the term value. For T4, we had R cubed, which is 1 less than the term value. So every single time we're finding the term value in a geometric sequence, the ratio is to the power of the term number minus 1. So if I wanted to write down T43, I'm going to have AR to the power of 42, because 42 is 1 less than the term number. I'm hoping that you're all with me. Please just take a second to take it all in. If I wanted to write term 100 in terms of A and R for a geometric sequence, T100 would be equal to AR to the power of 99. Why 99? Because 99 is 1 less than the actual term number. So please keep that in mind as we move on to our next few examples. Let's have a look at the next slide. Great, everybody. Let's have a look at this example. So we have been asked to consider the sequence an eighth, a quarter, a half, 1, going on to 128. Please note that if there's a full stop after a term of the pattern, that means that this is the last term of the pattern. So the first term is an eighth, and the last term of this pattern is 128. Let's have a look at the questions. So A has asked me to write down the fifth term of the sequence. B is asking me to determine a formula for the nth term of the sequence. C is asking me to determine the value of the seventh term. And then last but not least, I've been asked how many terms are there actually in the sequence. So I know that this is the value of the last term, but I want to know what is the position number of that term. Let's get going with A. Great, guys. So let's start with A. A is asking us to write down the fifth term of the sequence. So we're going to be thinking about certain strategies with patterns in order to see what type of pattern this is. If we're looking between the terms of an eighth, a quarter, a half, 1, I'm sure that everyone will agree with me that there isn't a common difference. And a common difference is the main property of an arithmetic sequence. Cool. I hope that everyone's still with me. We are going to be looking to see if there is a common ratio between the terms of the sequence. If there is a common ratio, then we can use the rules of a geometric sequence to continue asking or answering these questions. Let's go back to the board. So we have the common ratio, which we discussed earlier, is equal to term 2 over term 1, which will be equal to a quarter over an eighth. And a quarter over an eighth gives me an answer of 2. I can also check my common ratio by doing term 3 over term 2, which is 1/2 over a quarter, which will give me a common ratio of 2. So that means that between each term of this pattern, we have multiplied by 2. So in order to determine the value of term 5, I'm going to multiply by 2. So that means that the value of the fifth term of the sequence is in fact 2. Great, guys, let's move on to B. So we need to now determine a formula for the nth term of the sequence. We can see that A is an eighth just because that is the first term in a sequence. And my common ratio, which I found in A, is 2. For finding the nth term, we know that Tn is equal to A r to the power of n minus 1. So the nth term for the sequence will be Tn is equal to an eighth times 2 to the power of n minus 1. So that is my nth term for the sequence. Let's move on to C, everybody. We are doing well. Thank you for staying with me. I hope this is making sense. We now need to determine the value of the seventh term. Cool. I hope that everyone's with me that the value of the seventh term means that the term number for this example is 7. So n is 7. So what I have to do is substitute n is equal to 7 into Tn. This is going to allow me to find the actual value of the seventh term. Let's do the calculation together. So I'm substituting in 7 for n. So I'm going to have an eighth times 2 to the power of n minus 1. But please remember, I am substituting in n with 7. So I'm going to have that T7 is going to be equal to an eighth times 2 to the power of 6. Let us pop that into our calculator. So I've got 1 over 8 times 2 to the power of 6. So that means that term 7, whoopsie, sorry guys, term 7 is equal to 8. Great. D, I've been asked how many terms are in the sequence. That means that I'm looking for the n that matches the Tn of 128, because I know that is the last term of the sequence. So I'm going to have 128 is equal to an eighth times 2 to the power of n minus 1. I'm looking to solve for n. So the first thing I'm going to do, everybody, is to try and isolate the n. So I'm first going to say 128 divided by an eighth. Sorry, the fraction doesn't want to work for me, everybody. There we go. 1 over 8, which is going to give me 1,024. So my next line can be written as 1,024 is equal to 2 to the power of n minus 1. I'm going to ask you all to use your calculators to find the prime factors of 1,024, and I'm hoping that everyone will get 2 to the power of 10. So now if I'm solving this exponential equation, I can drop my bases, which means that 10 will be equal to n minus 1. If I move this negative 1 over, I'm going to have 11 is equal to n, which means that there are 11 terms in this sequence. Great, so now that we've looked at the introduction to geometric sequences, after the break we're going to look at more strategies for geometric sequences. See you soon. Welcome back, everybody. We've looked at the introduction to a geometric sequence. Now we're going to be looking at some more practical examples and strategies for solving geometric sequences. Before I get to the example, I just want to remind you of a few things just so we are all good for some examples. Let's have a look at the board. So please, can everyone just remind themselves that the nth term for geometric sequence can be written as Tn is equal to a r to the power of n minus 1. A reminder that a is the first term of a geometric sequence and r is my common ratio. My common ratio is the number or the factor that each term is multiplied by to get to the next term. So just a reminder that we can actually use this formula to write down term values in terms of a and r. So I can write term 43 as a r to the power of 42 because I always have the power being 1 less than the term number. So 42 is 1 less than 43. Cool, let's have a look at our example. So the first term of a geometric sequence is 3. Before I even continue reading this example, if I tell you that the first term of a geometric sequence is 3, we know that that means that T1 is equal to 3, and the first term is actually 3, so I can immediately tell that A is 3. Now we can continue reading our example. The sum of the second and the third term is 60. So we are now asked to determine the first 3 terms as well as the general term Tn. So I'm going to go through the working out now, but please just remember that as soon as you see a question that involves plenty of words and describing certain position numbers and position values, always make sure that you know what type of sequence it is, So for the one behind me, it's a geometric sequence. So I'm going to be writing my term values in terms of A and R. Being able to write my term values in terms of A and R will allow me to solve the equation simultaneously. So I'm going to write the term values in terms of A and R behind me, and then we are going to solve simultaneously. Let's have a look at the board. So we discussed that T1 is 3, and I know that term 1 always is A for a geometric sequence. So this simultaneous is actually quite nice because I immediately know what A is. So if I'm now going to be writing term 2 in terms of A and R, term 2 is actually the same thing as AR to the power of 1. Because just a reminder, the power of the R is always 1 less than the term value. This is being added to term 3, and I can actually write term 3 in terms of A and R as well. Term 3 will be AR squared, because R squared, the squared is 1 less than the term value. So I've got AR plus AR squared is equal to 60. We now have the advantage of having A being 3, so I can carry that across. So if I'm substituting in 3 for the A's, I'm going to have 3R plus 3R squared is equal to 60. In order to make my life a bit easier, I'm going to bring the 60 across to the left-hand side to create a quadratic equation. So I'm going to have 3R squared plus 3R minus 60 is equal to 0. I'm going to divide everything by 3. So I'm going to be left with R squared plus R minus 20 is equal to 0. Guys, I'm just going to move down here so I don't block anything. So if I factorize this quadratic equation, I'm looking for the factors of 20 that can create positive 1. So hopefully everyone will agree with me that I'm going to have R plus 5 and R minus 4. So this means that R will be equal to negative 5 or R will be equal to 4. So if I want to write a nice conclusion, I'm going to have A is equal to 3 and R is equal to negative 5 or R is equal to 4. Now we're going to actually answer the question. So just a reminder, I need the first 3 terms and I need the nth term. So when R is negative 5, we're going to have Tn is equal to 3 times negative 5 to the power of n minus 1. So that is my nth term for the pattern. The term or the first 3 terms of the sequence will be 3. 3 times negative 5 will give me negative 15 because my ratio is negative 5. And then if you want to use your calculator, we're going to have 3 times negative 5. And we're going to multiply again by negative 5 to get that the third term is 75. So the nth term when R is negative 5 and A is 3, we're going to have Tn is equal to 3 to the times negative 5 to the power of n minus 1. The first 3 terms are 3, negative 15, and 75. Then we are going to do when R is equal to 4, Tn will be equal to 3 times 4 to the power of n minus 1. The first 3 terms will be 3. 3 times 4 gives me 12, and 12 times 4 gives me 48. So that is the nth term and the first 3 terms when R is 4 and when A is 3. Wonderful, everyone. I hope that everyone's okay with the example that I've done so far. I've solved simultaneously for A and R. After the break, we're going to be looking at some more examples of geometric sequences. Welcome back, everyone. We are going to continue looking at different strategies to solve problems involving geometric sequences. Let's have a look at the next example together. So, guys, we have been given the geometric sequence 4x minus 3, x, 2x minus 5. Just something that I want to highlight right at the beginning is I've been told that it is a geometric sequence. So when I've been told that it is a geometric sequence, I know that there has to be a common ratio involved, because we know that is the main property of a geometric sequence. So we need to now determine the values of x for which these terms form a geometric sequence or geometric sequences. Then B is asking me to determine the formula for the nth term of each sequence. So the question has kind of also given me a clue that there's going to be more than one value of x. Let's try and work out x together. So we have the first three terms, and I've been told that it is a geometric sequence. On the slide before, I mentioned to you guys that we know that the geometric sequence property is the fact that there is a common ratio. I'm going to use the fact that there actually is a common ratio in order to solve for x. How can I do that? I know that the common ratio is equal to term 2 over term 1, but I also know I can write the common ratio is equal to term 3 over term 2. Now, if you're wondering, how is this going to help me? This is going to help me because I'm going to end up with two different expressions for the ratio that involve x's, but I know that the common ratio of a geometric sequence is the common ratio. It's called the common ratio because it's common. So that means that I can equate them because they have to be equal, because I know the ratio is in fact common. Being able to equate them means that I can actually solve for x. So let's solve for x together. So I'm going to substitute in term 2 over term 1, which is going to give me x over 4x minus 3. Then I'm going to substitute in term 3 over term 2, which is 2x minus 5 over x. As I mentioned, the ratios are common, so I can equate these two expressions to each other. So I know that x over 4x minus 3 has to be equal to 2x minus 5 over x. I'm going to do some cross multiplication over here in order to solve for x. So I'm going to have x squared is equal to 2x minus 5 times 4x minus 3, which means I'm going to have x squared is equal to, if we do FOIL or however else you know how to multiply binomials together, you're going to end up with 8x squared minus 20x minus 6x plus 15. Then what I'm going to do is I'm going to take this x squared over to the right-hand side. So I'm going to have 0 is equal to 7x squared minus 26x plus 15. Great, so now we are going to actually factorize to see what the values of x are going to be. What I need to do is I need to know what 7 times 15 is. And I need to use those factors to create negative 26. So let's see what happens when I divide. Oh, let's have a look. So that means that x will be equal to 5 over 7, or x will be equal to 3. Wonderful, everyone. So far I have done A. I have solved for x. Now I'm going to look at the second part of this question, knowing that I actually have two x values. Let's look at the next slide together. So I know that my two x values are x is equal to 3 and x is equal to 5 over 7. The question for B is asking me to determine the formula for the nth term of each sequence. And I'm only going to be able to determine the nth term for each sequence by actually substituting in the respective x values, as substituting in the respective x values will actually be able to help me find A and R. So for each case, I'm going to substitute in x is equal to 3 for the pattern. So I'm going to have 4 times 3 minus 3 for term 1. I know that 3 will be the value of term 2, and 2 times 3 minus 5 will be the third term of the pattern. I'm going to do the exact same thing for when x is 5 over 7. I'm going to have 4 times 5 over 7 minus 3. For term 2, I know that it will have a value of 5 over 7. Then for term 3, I'm going to have 2 times 5 over 7 minus 5. So all that I've done is I've substituted in the respective x values to find the first 3 terms of the patterns. I'm going to ask you guys to do that for yourselves. And you should get that when x is 5 over 7, the pattern goes negative a seventh, then 5 over 7, then negative 25 over 7. Then when x is 3, we should have the pattern going 9, 3, then 1. Just a reminder, I'm looking for the nth term of these patterns. So I want to write these patterns in terms of Tn is equal to A to R to the power of n minus 1. So for when x is 5 over 7, I can see that A is equal to negative a seventh. R is actually equal to negative 5, because I can see that between each of these terms, there's been a multiplication of negative 5. So you can use the R formula in order to do that and check it. I have time constraints, so I am going to continue. So Tn will be equal to negative a seventh times negative 5 to the power of n minus 1. Looking at the example when x is 3, I can see that A is equal to 9. My common ratio is going to be a third. Why, you may ask, is because between each term I've multiplied by a third, and multiplying by a third is actually the exact same thing as dividing by 3. So Tn will be equal to n, or A, which is 9, times a third to the power of n minus 1. So that's the end of that question, everybody. We're now going to look at the next example. The next example is going to require your knowledge of arithmetic sequences as well as geometric sequences. I'm going to ask you to remind yourself that an arithmetic sequence has a common difference and a geometric sequence has a common ratio. We're going to use both of these pieces of information to solve this question. Let's have a look at the question together. So, the first 3 terms of the sequence 6xy 16 form an arithmetic progression, and the last 3 terms form a geometric progression. So A is asking me to first determine the values of x and y. B is asking me to state the arithmetic and geometric sequence for each of these solutions. So please remember the first three terms are arithmetic, so that's your common difference. The last three terms are geometric, which means it's going to be a common ratio. Please note I've just wrote CD for shorthand for common difference and CR for common ratio shorthand. So we need to determine X and Y. These three are arithmetic and the last three are geometric. And the fact that I have an X and a Y means that I'm going to be doing some simultaneous solving. So, everyone, an arithmetic sequence has common difference as its main property, and geometric sequence has common ratio as its property. We are going to then create expressions involving X and Y using the fact that it's an arithmetic combined with a geometric sequence in order to solve for X and Y. I'm going to go through it step by step. Please just stay with me. I know it's a lot, but you've got this. So, we know that these three will have a common difference. So we know that term 2 minus term 1 will be equal to term 3 minus term 2, because we know that the common differences of an arithmetic sequence are equal to each other. So that means that X minus 6 will be equal to Y minus X. Immediately what I'm going to do is I'm going to isolate Y by taking this negative X over. So I'm going to have that 2X minus 6 is equal to Y. Then using my knowledge about geometric sequences, I know that if this is term 2, term 3, and term 4, term 3 over term 2 will be equal to term 4 over term 3. So Y over X will be equal to 16 over Y. I'm going to do some cross multiplication so I can see that Y squared will be equal to 16x. I'm now going to take this 2x over, or the y over rather. Let me just erase that, everyone. Great, guys. So now I'm going to take this y across. So I'm going to have 2x minus 6 squared is equal to 16x. If I multiply those two binomials out, I'm going to be left with 4x squared minus 24x plus 36 is equal to 16x. I'm now going to move the 16x over to the left-hand side, so I'm going to have 4x squared minus 40x plus 36. To make this trinomial a bit easier, everyone, I'm going to divide by 4, so I'm going to have x squared minus 10x plus 9. This trinomial can be factorized to be x minus 9, x minus 1. So x is equal to 9, or x is equal to 1. I now just need to find the corresponding y values. So when x is equal to 9, I'm going to have 2 times 9 minus 6 is equal to y. So that means that 12 will be equal to y. Then when x is equal to 1, I'm going to have 2 times 1 minus 6 is equal to y, which means I'm going to have negative 4 is equal to y. So we've got the two pairs. X is equal to 9 goes with 12 is equal to y, and x is equal to 1 goes with negative 4 is equal to y. So we are now going to write down the individual sequences. We have the arithmetic sequences, which are the first three terms, so it's going to be 6. Then using the first option, it's going to go 6, 1, negative 4. Using the second option, it's going to be 6, 9, 12. Just remember, I'm substituting in x and y. The geometric sequences are the last three, so this is going to be 1, negative 4, then 16. Then using 9 and 12, it's going to be 9, 12, 16. Great, thank you so much for joining me today, everyone. I hope that geometric sequences are making more sense, but I look forward to seeing you next time. I hope you have a great day.